So let's look at a couple of different gas laws. And the first law that we're going to look at is Avogadro's law. And Avogadro's law is the relationship between volume and N, where N is the number of moles. They are directly proportional, so it's a direct relationship. As volume increases, the number of moles increase. As volume decreases, the number of moles decrease. And this is important because if I keep pressure and temperature constant, then if I have an equal volume of gases, regardless of what the gas is, so maybe I have an equal volume of carbon dioxide and an equal volume of nitrogen gas, both of those, because their volumes are the same, would have the same number of moles of gas. And this is important. I have seen questions on the exam that you will take in May that are directly related to this critical thinking questions, okay? Let's look at Boyle's law. This is the relationship between pressure and volume. So as pressure decreases, a volume increases. And as pressure increases, volume decreases. So it is an indirect relationship. And an example of Boyle's law would be a suction cup. So here I have this little suction cup, and the suction cup on the bottom part has this concave, and there is air inside of this. All right, so the way a suction cup works is if I take this suction cup and I press it down, I am decreasing the volume of air. So I'm decreasing the volume of air. The air's still there, I'm just decreasing its volume, which causes the pressure outside to increase, and my suction cup now sticks to whatever surface I have it stuck to. All right, so Boyle's law is the good example of how suction cups work. Then we have Charles's law. And Charles's law is the relationship between volume and temperature. This is if volume increases, then the temperature increases. If volume decreases, the temperature decreases. So it is a direct relationship. And an example of this would be like a hot air balloon. So the way a hot air balloon rises into the atmosphere is they increase the temperature of the air in the balloon. This causes the balloon to expand, and then the balloon flies up into the atmosphere, and here's my hot air balloon, all right? And here's the ground. And then the way we're going to get our hot air balloon to come back down to the ground, we're going to lower the temperature in the balloon, all right? By lowering the temperature in the balloon, the volume of the balloon decreases, causing the balloon to come back down to Earth, volume and temperature. Our final one would be Gay-Lussac's law. And now each one of these laws is named after the scientist who discovered it. All right, so this is the relationship between temperature and pressure. All right, and again, this is a direct relationship. So if temperature increases, pressure increases. And if temperature decreases, pressure decreases. And an example of this would be tire pressure. All right, so in the summertime, well, let's start with the winter. In the wintertime, the temperature goes down. It gets cooler outside, which means the pressure of the tire on your car also decreases. This is why in the wintertime, your air light goes off, your tire pressure light goes off, okay? Because the temperature has decreased, so the pressure decreases. So you have to go and get some air in your tire in order to adjust for that. In the summertime, as the temperatures warm up, the pressure of the air in the tire increases, so you actually should be letting air out of your tire in the summertime to adjust for that. And you need to make sure that you follow whatever manufacturer label there is on your tire, because each tire is different. So you have to adjust the air in your tires according to whatever that manufacturer label is. So now that we have our four different laws, This is going to be our PVTn problem worksheet that I've posted on Canvas. And let's look at number 1. Okay, so it says, what would the new pressure be if 250 centimeters cubed of gas at standard pressure is compressed to a volume of 150 centimeters cubed and N and T are constant? Okay, so when we set up our chart here, we have our P, T, V, N. All right, so we have our initial, we have our final, and then we have our effect, what happens. So it tells us that the number of moles are constant and the temperature is kept constant. So our volume initially is 250 centimeters cubed, and then it goes down to 150 centimeters cubed. So I am seeing a decrease in volume. So if I see a decrease in volume, that is going to cause an increase in pressure. So it tells us that our pressure is at a standard pressure. So let's use atmospheres. All right, you can do this with any pressure, but I'm going to use atmospheres. And I've already know that the standard atmospheric pressure is 1, so 1 atmosphere. So here's how I'm going to set this up. This is what I want right here. I'm going to take my 1 atmosphere, and I'm going to set it up as a ratio, essentially. If I want my pressure to go up, I have 2 options. I can put 250 on top and 150 on bottom, or I can put 150 on top and 250 on bottom. So essentially this is a ratio, and we know that ratios can have reciprocals, okay? We can just make the reciprocal. So the question becomes, which one of these 2 is going to make my pressure go up? And that's going to be this one. 1 times 250 divided by 150 is going to give me an increase. So this is not the one I want. So we're going to set it up such that it causes the effect that we want. If I wanted pressure to go down, then this is the ratio I would have used. But because I want pressure to go up, this is the ratio I use. All right. And so when I plug this into my calculator, I find 1.67 atmospheres. And again, we're still following the rule of 3. All right. Let's do a more challenging one from this worksheet, number 4. We have our pressure, our temperature, our volume, our number of moles, initial, final, effect. Okay, so when I look at number 4, I want to know the new volume if 250 centimeters cubed of gas at 25 degrees Celsius and 730 millimeters of pressure. Now, I'm going to stop right here for a minute. I'm going to stop right here. My problem gives me a temperature of 25 degrees Celsius. Now, when we solve gas problems, we must use Kelvin. So we have to convert 25 degrees Celsius into Kelvin by adding 273. So when we do that, we find 298 Kelvin. Temperature has to be in Kelvin. And then it says we are changing to standard temperature and pressure. So if this is millimeters of mercury and this is my Kelvin, I need to go to standard. What is my standard for millimeters of mercury? 760. And what is my standard temperature in Kelvin? I added 273. That is my standard. So I'm looking for my new volume. So to set this up, what happened to pressure? My pressure went up. So if I see an increase in pressure, what's going to happen to volume? Volume is going to decrease. So let's go ahead and start setting this up. My volume is 250 centimeters cubed. To get a lower volume, I'm going to have to put the smaller number on top, 730, divided by 760, setting it up as a ratio. Now I have a second part. This second part is independent of the first part. My temperature went down. So a decrease in temperature is going to cause a decrease in volume. So how am I going to set up this ratio such that 250 goes down? All right, so I have a second part here basically. All right, so I'm basically got a second part here. So to go down, I'm going to put 273 on top and 298 on the bottom of my ratio. So now here's how I've got it set up, okay? So at this point, I can now solve 250 times 730 times 273 in parentheses divided by another parentheses 760 times 298. So when I put this into my calculator, I get, let me plug this in real quick. I get 219.98. Now using our rule of 3, that is going to be 220 with a decimal place to lock in that 0 centimeters cubed. So the overall effect here was a decrease in volume. All right, I started at 250 and I ended at 220. So each one of these are independent of each other to cause some sort of overall effect. It's possible that this volume could go up, but the overall effect goes down. It just depends on what values you're given within that problem.